In this video, we prove Yosida's extension of von Neumann's theorem, extending it from the realm of Hilbert spaces to the context of reflexive Banach spaces. The statement of the theorem is the same in that level of generality. You look at bounded linear maps that are contraction, and you can split the space into the null space of identity minus t and the closure of the range, and as a consequence of this splitting, you prove a mean ergodic theorem, that is to say a convergence in the strong operator topology of the Cesaro mean of the powers of t to the projection onto the null space of identity minus t. Now, if you remember how we did that for the Hilbert space case, we exploited lemma 14.3. So we exploited that splitting after having proven that splitting, proving the theorem was not too hard. And to prove that splitting, we really exploited the fact that every closed subspace in a Hilbert space is a complement. And that's certainly not true in general reflexive Banach spaces. So we won't be able to just say this has to have a complement and then identify the complement by computing the perp and showing that it's the closure of the range. We can do that, but in order to construct projection onto subspaces or even sometimes onto convex sets in reflexive Banach spaces, we know that we can exploit Banach-Alaoglu theorem, extract converging subsequences for the weak topology from bounded sequences and construct the projection as a limit. Now, this is going to give us something in the sense of the weak topology. In order to move back to something about the strong topology, what we should use is Mazur's theorem that tells us that weak closure of convex sets are strong closures of convex set, and convexity will be all over the place here because the mere idea of a Cesaro average is really about taking convex combinations of the power of t. Now, on our way to proving Yosida's version of von Neumann theorem, we will first prove another theorem of Yosida, which is a Tauberian theorem, that really put these techniques exploiting weak convergence into effect. And it's a Tauberian theorem which refers to, a family of theorems that allow you to move from one form of convergence to another form of convergence, very globally speaking. So what does the theorem 14.4 tell us in the context of contraction on a general Banach space? It tells us that the following assertions are equivalent. So convergence of the Cesaro mean of the powers of t applied to an x to some vector, which is really the sort of thing we're looking for, is equivalent to weak convergence of the same thing. That's the equivalence between 2 and 3. And in fact, it's also equivalent to just weak convergence of even just a subsequence. So this is a much weaker statement than 2 on the face of it, but we will see that this is equivalent, and this is very good news for us, of course, because weakly converging subsequence is something that reflexivity is going to give us. And then we have 1 which turns out to be equivalent to all of that. So if you're a limit of Cesaro mean or of powers of t, you have to be in a null space of identity minus t. And if you're a limit of such convex combination, well, you are in the closure of the convex hull of all the powers of t. But again, the striking point is that 1 is equivalent to all of that. So if you are getting to the null space by taking limits of any convex combinations of the powers of Tn, then this particular choice of convex combination, the Cesaro average, will have to converge. So this is like going from arbitrary, if you go 1 to 2 side, you're going from arbitrary convex combination to this particular choice of convex combination. And all of these things are equivalent. So this is the key technical thing we need to prove. And then from that, we'll construct the projection onto the null space, and then the proof of the Yosida extension of von Neumann theorem will look very similar to the proof of von Neumann theorem itself. So let's start with the Tauberian theorem, theorem 14.4. Okay, so let's start with 1 implies 2. So we take a y, which is in the null space of identity minus t, and it's also in the closure of the convex hull of the powers of t applied to x. Okay, so for such a y, first of all, I'm going to pick a z. I'm going to give myself an epsilon, and I'm going to pick a z that is properly in the convex hull, and which is within epsilon of y. And so there exists an n in n, and there exists a sequence of coefficients ck in 0, 1, such that the sum of the ck is 1, and the sum of the ck tk of x is z. Okay, now what do I need to estimate? I need to give myself an n, which I'm going to send to infinity, and I need to look at y minus the Chern averages of t and x. Okay, so now what I'm going to do is that, first of all, I'm going to use the fact that y is in the null space of I minus t, and therefore this is really the same thing as 1 j equal 1 to n tj of y, because tj of y is just y, minus tj of x. Okay, and then I'm going to use triangle inequality and introduce the z. So I'm going to get sum j equal 1 to n tj of y minus z plus 1 upon n sum j equal 1 to n tj of y minus tj of z minus tj of x. Okay, so for the first one, I'm just going to use triangle inequality again, and the fact that t has norm less than 1 as an operator, so this is smaller than the norm of y minus z. And then for the second one, I'm going to introduce the convex combination, and so I can write this entire thing as the sum k equal 1 to capital N of 1 upon n sum j equal 1 to n of tj of z, which is the sum of tkx, and then I get this minus tj of x. Okay, now y minus z is smaller than epsilon, and here I lost my ck. I'm going to use triangle inequality again, get the convex combination out, and then inside here I get, again just by triangle inequality, I get, so the first sum is the sum j equal k plus 1 to n plus k of tj of x, and the second sum is the sum j equal 1 to k of tj of x, and the point is that that's to n plus k, and the point of all of that is that there's k elements in this sum, k elements in this sum, and so this entire thing here is smaller than epsilon, plus the sum k equal 1 to capital N of k 2k times ck divided by n times the norm of x, because the norm of t to the j is always smaller than 1. So this entire thing is smaller than epsilon plus capital 2 capital N divided by n times the norm of x times the sum of the ck. But the sum of the ck is 1. So this entire thing is epsilon plus 2 capital N divided by n times the norm of x. If you send n to infinity, then this goes to epsilon, and epsilon was arbitrary. So the limit of y minus the Chern average of tjx has to go to 0 as n goes to infinity. So that proves 1 implies 2. So we've proven 1 implies 2. 2 implies 3 is obvious because strong convergence implies weak convergence, and 3 implies 4 is obvious because convergence for all natural numbers implies convergence for a subsequence. So the only thing that we still have to prove is 4 implies 1. Let's do that now. Okay, so we have that y is the limit, the weak limit of 1 upon nk sum j equal 1 to nk of tj x as k goes to infinity. So this gives us that y belongs to the weak closure of the convex hull of the Tn, right, because the Chern average is certainly a convex combination of powers of T. Now, it's in the weak closure, and the convexel is obviously a convex set. So by Mazur theorem, we have that Y belongs to the strong closure, because the strong and the weak closures are the same thing. So all we have to show now is that Y is in the null space of identity minus T. So let's give ourselves an epsilon, and we can pick a capital K, let's say in N, such that for all little k greater than capital K, Y minus 1 upon nk sum j equal 1 to nk of tjx x star is smaller than epsilon. Let's do that for any x star. So let's give ourselves an x star. And then I'm also going to ask, we'll see why in a minute, for this to be small tested against t star of x star, which I can because the series converges, this series here converges to y weakly. So I can test on x star or t star of x star. Okay, having picked these two things, I'm going to look at y minus t of y x star. And I want to show that this is 0, irrespective of the choice of x star, and so that will give me that y is in the null space of identity minus t. So let me introduce the things that we know. So I'm going to introduce, for k greater than capital K, this Chezaro averages. Okay, use triangle inequality, so I have to subtract from that. The same thing applies to t of y. And then I also have this tj plus 1 minus t of y x star. Now, on that last term, I can bring a t to the x star, and I can use the condition here. And on the first term, I can use the condition there. So the first term is controlled by epsilon, the third term is controlled by epsilon, and I'm left with the middle term. But in the middle term, I have a lot of cancellation, because I could rewrite that sum as a sum starting at 2 and going to nk plus 1. So really what I have left in the second sum is purely 1 upon nk times t of x minus 1 upon nk times t nk plus 1 of x, tested on x star. And now this is smaller than 2 epsilon plus norm of x star divided by nk times twice the norm of x, say, because norm of t has norm less than 1. This is true for every k, so I can send k to infinity. So this tends to 2 epsilon as k goes to infinity. And epsilon was arbitrary. So y minus ty x star is 0 for all x star in capital X star. So y is in the null space of identity minus t. And that concludes the proof of theorem 14.4, the Tauberian theorem. Okay, so we're now in the position to use theorem 14.4 to prove theorem 14.5, the actual extension of von Neumann theorem by Yosida to reflexive Banach spaces. So in order to do that, okay, let's give ourselves an x in our Banach space, and notice that 1 upon n sum j equal 1 to n of tj of x in norm is always going to be smaller than the norm of x, because the norm of t is smaller than 1, and that's for all n in n star. So we have a bounded sequence, therefore by reflexivity, well, I can extract a weakly converging subsequence from that bounded sequence. So 4 from theorem 14.4 holds. Okay, so we have y, the weak limit of this Chezaro averages over a subsequence. And so because 4 holds, well, 1 and to hold from theorem 14.4. So y has to be the limit of 1 upon n sum j equal 1 to n tjx. So that exists. So we have strong convergence of the Cheshire averages, and we have the fact that y is in the null space of identity minus t. So we can define p of x to be this limit, which we know exists for any x, and we can remark that p of x belongs to the null space of identity minus t for all x in x. Now what we want to show is that this p is actually the projection onto the null space. The first thing to remark is that the range of p is really the null space of identity minus t. We've seen one inclusion, but the other inclusion is trivial, because if you have an x in the null space, then it is equal to any Cheshire averages, because Tj of x is just x itself for all n. So obviously it is a limit of such things. So, okay, so the range of p is the null space of I minus t. And also as a consequence of that, we have p square equal p, because if you look at something that is already such a limit, then it is in the null space. So we have that 1 upon n sum j equal 1 to n of tj of p of x is equal to p of x for all n in n and for all x in x for that matter. So p square has to be equal to p. Now that tells me that the range of identity minus p intersected the range of p has to be trivial, because if p of x, say, is equal to 1 minus p of y, then I have that p of x is equal to p minus p square of y, which is 0. Okay, and on top of that, of course, any x in x can be written as p of x plus identity minus p of x. So we have that x really splits into the range of p and the range of identity minus p. Maybe closure of that if this is not closed. And we've seen that the range of p is the null space of identity minus t. So what we have is a splitting between the null space of identity minus t and the range of identity minus p, which we know exists now. So what we need to show to conclude the proof really is just that the range of identity minus p closure is the same as the range of identity minus t closure. Alright, so let's do one inclusion first. Let's do this inclusion. So if I take a x in x and I look at identity minus t of x, and I want to show that it's in the closure of the range of I minus p, then that should be fairly easy, because I have that p of I minus t of x is the limit as n goes to infinity of 1 upon n sum j equal 1 to n of tj minus tj plus 1 of x. Now this sum telescopes, and what I get is the limit of 1 upon n norm t of x minus tn plus 1 of x, and this is smaller than the limit of 2 norm of x divided by n, which is 0. Okay, so p of identity minus t of x is 0, so x is identity minus p of, so identity minus t of x is identity minus p of identity minus t of x plus p of identity minus t of x, and we know that this is 0, so this means that the range of identity minus t is included in the range of identity minus p, and then if you take closure, then you still have the inclusion. So that gives us one inclusion. Now to go the other direction, I'm going to introduce a intermediate subspace that I'm going to use. So I'm going to define, let's call that n lower star, and n lower star will be the null space of identity minus t star. Remember, in the Hilbertian case, we knew that this null space was nothing but the null space of identity minus t, but here, of course, the adjoint acts on a different space compared to the operator t itself. So this is really a subspace, of course, of the dual x star. Now, we're going to show that the range of identity minus p closure is included in the perp of that n star, and then we're going to show that the perp of that n star is included in the range of identity minus t closure. Okay, so let's take a x in capital X, and let's take an x star in n star, and let's have a look at identity minus p applied to x, and then test that on x star. Now this is x star minus the limit of 1 upon n sum j equal 1 to n of t to the j applied to x, and then test on x star as n goes to infinity. Now I can pass to adjoints, and I get that minus x. There's a limit here. 1 upon n sum j equal 1 to n of t star j applied to x star. Okay, but x star is in the null space of identity minus t star. So t star j of x star is nothing but x star. So this entire thing is just x star minus x star. It's actually true for every n. You don't even need to pass to the limit. So this has to be 0. So we've proven what? We've proven that the range of identity minus p is certainly in the perp of n star. And so you can pass to closure. The perp is always closed, and you have this inclusion. Okay, now for the other inclusion, let's proceed by contradiction and assume that the perp of n star is not included in the closure of the range of identity minus t. Then I can use Banach, and I can pick a point to start with x in n star perp. Now notice that n star perp is included in x, right? A priori it should be included in x double star, but I'm in a reflexive Banach space, so I can make that identification. And then by Banach I can separate that point x from the subspace closure of the range of identity minus t. That is to say, there exists an element, y star, in the dual, such that y star is 0 for all y in the closure of the range. The alpha in the definition of the hyperplane has to be 0 when I'm separating from a subspace, and then y star applied to x has to be non-zero. Right, so I can find a functional that separates that point x from the subspace range of IT. But that is unlikely to happen, because then for any z in x, if I look at I minus t z and I test that on y star, for that y star that gives me the separation, what do I get? I get that this is the same as z identity minus t star of y star. Okay, but then it has to be 0 because, okay, y star tested on identity minus t of z is 0 because y star tested on any y in the closure of the range even is 0. So for all z in x, I minus t star of y star tested on z here has to be 0. And what does that tell me? That tells me that y star is in n star, and thus y star x has to be 0, which is a contradiction because in the meantime y star x would have to be non-zero here. So this is a contradiction, and this concludes the proof, right? We have proven that x split into the null space of identity minus t and the range of identity minus t, and we have proven that the projection onto that range, let's call that p, applied to a point x will always be the limit of the Cesaro averages of the powers of t applied to x for all x in x. This defines the projection onto the null space of identity minus t, which is also exactly the range of that operator P. That concludes the proof of Yosida's extension of von Neumann theorem from Hilbert spaces to reflexive Banach spaces. And we've seen all our tools coming from analysis in reflexive Banach spaces come into action. Mazur theorem, Banach-Alaoglu theorem, and its appropriate consequences in reflexive Banach spaces, weakly converging subsequences of bounded sequence, and the Banach theorem.